Let's solve some problems with angled projectiles. Now we're going to use the exact same problem-solving process that we have done for the rest of this unit, which means that we need to start with an XY table of knowns. Now the first problem says an object is launched at a velocity of 50 meters per second at an angle of 35 degrees above the horizontal. So what can we put into our table of knowns right off the bat? Well, we could say that our x velocity is 50 cosine of 35, because we now know that we need to take that initial velocity, break it up into x and y components. So that means that the y component of the initial velocity is 50 sine of 35. Now, those are the only numbers that were given, but we can read into the problem and get some implicit information that is not directly told to us. Things like the fact that the acceleration must be acceleration due to gravity, so that's negative 9.8 meters per second squared. We also can assume from the problem statement that our change in height must be 0. We must be shooting from the ground and landing on the ground. And the reason why we can make this assumption is because if we were not shooting from the ground and landing on the ground, they would have to tell us where we landed and how high above or below our starting point that is. Since we are not given that information, we assume that that delta y is going to be 0 meters. Which then just leaves the time in the air as a question mark. And of course, the time in the air is a question mark for both our x and y. And it does appear that we are given no information about the range of this object, so our delta x is going to be a question mark as well. Part A asked us to please find the time that the object is in the air. So we look at our xy table and we say, well, we only have one unknown on the y side, and that is the time. So let's use everything we know about y in order to figure out what this time is going to be. So vi delta t plus 1/2 a delta t squared. And now we can fill in everything we know. Our delta y is 0 meters. Our vi is 50 sine of 35 times delta t plus 1/2 times negative 9.8 meters per second squared times delta t squared. Now, if you notice, we have delta t in 2 of the terms. So why don't we take our second term, since this is going to be negative 4.9 delta t squared anyway, let's just add that to the other side so that we end up seeing a 4.9 delta t squared is equal to 50 sine of 35 delta t. Now, when we look at this, we see that we have delta t in all of the terms in this equation, which means that we should be able to divide delta t out in order to make our equation a little bit more simple. So the squared goes away from the left-hand side, and the delta t goes away from the right-hand side, and we are left with 4.9 delta t equals 50 sine of 35. So to solve for delta t, we just divide both sides by 4.9. And we find that our time in the air is going to be 5.85 seconds. So we can even put that into our table of knowns now, 5.85 seconds. Now we need to find the range of the object, so we need to find that delta x. Well, the equation that we have for the x direction is good old delta x equals v delta t. So we can put in 50 cosine of 35 as our v. We'll put in that 5.85 seconds as our t. And when you throw that into your calculator, you find that the delta x must be 239.6 meters. Now, part C is a very interesting question because this is not a question that we got when we were looking at horizontal projectiles. Find the maximum height the object reaches. Now, we don't really know anything about the height right now. The only thing we know is that from the start to the end, we have a delta y of 0. But if we go back to the notes that we took last time, we have a couple cheats for when the delta y is 0. Things like the time to the peak is half of the total time. Well, we know the total time. The total time is 5.85 seconds. So that means that the time it takes for me to get to the peak of motion must be half of 5.85 seconds. And I could probably use that information to help me solve this problem. So I'll go back to my good old delta y equation. Delta y equals vi delta t plus 1/2 a delta t squared. And since I'm solving for that delta y, we'll keep it alone, we'll not touch it. But for vi, we'll put in 50 sine of 35. And then for that delta t, we're going to cut that total time in half. So 5.85 over 2 plus 1/2 times our acceleration of negative 9.8 meters per second squared times delta t, which is 5.85 over 2, and we square that. Now look at that. It's beautiful. Everything on the right-hand side of our equation is a number. We just need to throw it into our calculator. And if you throw it into your calculator, you find that your delta y is going to be 41.5 meters. So the highest height that this object reaches through its flight is 41.5 meters. Now I'm going to show you another way to do that problem. We were able to utilize some very special knowledge that is particular to the fact that our delta y was 0 in this problem. But what if your delta y is not 0 and you are asked to find the maximum height that the object reaches? Well, now we have to think about something else we might know at that maximum height. We are pretending like we cannot assume that the time to the peak is half of the total time. So instead we have to think about other things about that peak, like perhaps the fact that the y velocity at the peak is going to be 0. So we could use vf squared equals vi squared plus 2a delta y to solve this problem, because we know that this vf at the peak is going to be 0. Again, it's not to say that the total velocity is 0 at the peak. It's just the y component of the velocity that is 0 at the peak. So we'll have 0 squared equals 50 sine of 35 squared plus 2 times negative 9.8 times delta y. And when you do the algebra to solve for delta y, you find that you get the exact same number. Delta y is 41.5 meters. So this is very interesting for us to know, because this equation here allows us to solve for the maximum height of an object at any point. This works for any kind of angled projectile, and not just angled projectiles where the starting and ending height are the same, which means your delta y is 0. Vf squared equals vi squared plus 2a delta y will always work. Let's do a second exercise just to get this down pat. A basketball player shoots the ball at a speed of 10 meters per second at an angle of 60 degrees and makes the shot. If the rim is 1.5 meters above the hands of the player, how far is the player standing from the basket? So let's just draw a quick picture here so that we are sure that we understand what the problem is saying. So we have a basketball hoop. Maybe it looks something like that. And we got a basketball player who maybe looks a little bit like this. He's holding the basketball. He's going to shoot that basketball and try to make this shot. So beautiful. There's that beautiful parabolic shape. Okay, so now that we visualize the problem, let's make an XY table of knowns. Player shoots the ball at a speed of 10 meters per second at an angle of 60 degrees, so that allows us to fill in our velocities. X velocity will be 10 cosine of 60. The y velocity is going to be 10 sine of 60. The rim is 1.5 meters above the hands of the player. So if we kind of imagine where this rim is, then from the hands of the player to the rim will be our delta y. And since that is above where we started, that's going to be a positive delta y. So we'll have a positive 1.6 meters in right there. Those are all the numbers that they give us in the problem. So let's start filling in the numbers that we implicitly know are a part of this problem. Things like acceleration is negative 9.8 meters per second squared. We do not know the time. That time goes into both columns. And then at the end of the day, this problem is going to ask us how far away the player is standing from the basket. So at the end of the day, this problem really is asking us, what is this delta x? Okay, cool. When we look at this XY table of knowns, we say, well, we've got 2 question marks in the x direction, but only 1 question mark in the y direction. So let's start by using the y direction in order to find out what that time in the air is. So delta y equals vi delta t plus 1/2 a delta t squared. Our delta y is 1.6 meters, so that has to equal 10 sine of 60 times delta t plus 1/2 times negative 9.8 meters per second squared, delta t squared. If we look at this, this is very interesting for us, right? Because we've got a delta t squared, we got a delta t, and then we got no delta t. That screams quadratic equation to me. This is harking back to what we talked about in that last lecture when we talked about what problem solving looks like when we start and end at different heights. If you start low and you end high, like how we do in this basketball problem, you must solve a quadratic equation to find the delta t. And that is the situation we find ourselves in right now. What happened? Oh, there we go. So let's rewrite this equation a little bit so that it looks a little bit more like a quadratic equation. So we're going to subtract this 1.6 to the other side, and we're going to write 0 equals negative 4.9 delta t squared plus 10 sine of 60 times delta t minus 1.6. And that is the ABC form of a quadratic equation that we are very used to. Now, there are a couple ways that you can solve quadratic equations, right? Number 1, you could do factoring. Number 2, you could use the quadratic formula. Or number 3, you could solve this by graphing. Now, I have to tell you, only 2 of these 3 methods for solving quadratic equations is going to work consistently in this class. Factoring does not work very well because factoring requires very pretty numbers in order to work. And do we have very pretty numbers here? No way. We never have pretty numbers in physics class. So we're really stuck with using either the quadratic formula or graphing in order to solve a quadratic equation. If you need to practice solving quadratic equations, because we kind of forgot how to do this, then you need to search out resources on how to solve quadratic equations, okay? I'm not going to go through it on this video. You'll have to seek that out yourself. Instead, I'm just going to say that my favorite method of doing this is by graphing. So when I plug this equation that we have up here into my y equals, I search and use the calc button in order to find where my line crosses the x-axis. That's how I can get that the time in the air is going to be 1.573 seconds. Now that I have that the time is 1.573 seconds, let's add that to our XY table of knowns. Oops, this one. 1.573 seconds. Now I've got everything that I need in order to find delta x. So we'll finish this problem by using good old delta x equals v delta t. We'll substitute in 10 cosine of 60 as our v. We'll substitute in 1.573 as our delta t. And then we'll put it into our calculator and find that the delta x must be 7.865 meters. As you can see from these two example problems, the problem-solving process for angled projectiles is exactly the same as what it is for horizontal projectiles. We need to use one dimension to find the time in the air, and then using that time in the air, we answer whatever the question is asking us. So if you felt very comfortable solving horizontal projectile problems, you should feel very comfortable solving these angled projectile problems.